So these are my first draft of notes, so I'm going to have typos. So here's a typo here. So anyway, if you guys find typos, please let me know on the discussion board. I'll post a little section where you guys can post some for extra credit. And I've done that before for my other classes as well. Okay, so here's where we're going to review some of the things from last quarter and then build on that by talking in the context of alkynes. Okay, we know how to make alkenes because you can take a leaving group and with a strong base you can lose a beta hydrogen. And what I mean by beta hydrogen is this is alpha to the leaving group, this is beta to the leaving group. Alpha is directly attached, beta is next door. Okay, so you take the base and you grab this H, make the alkene pi bond, and then you have a leaving group that leaves. And this is called an E2 elimination. That means this is all happening simultaneously, and it happens best when it's antiperiplanar, and it happens best under heated condition, high heat. So now we want to try to figure out, is there a way to make alkynes that way? Well, you need to make another pi bond, so we need to do another elimination. I call it double elimination. So usually we use this very strong base like sodium amide. Okay, so this is amide or amide, and we use the amide ion to pick off this H. So I'm going to do, and sodium part doesn't matter so much, so I'm going to take the sodium amide, I'm going to do this, and then I'm going to have another one come in, so let's do this one first. So this is just regular E2 elimination, right? Alright, do you guys see how I did that? So I just took this H off, I made ammonia, and then I've got the rest of this still there. So, and I also lost a bromide. So now do you guys see I can also keep going because I have a strong enough base, amide, I can take the amide ion and I can react it again, pulling this one off because I have now another beta hydrogen available. Now why am I using sodium amide? Well, think back to what we said over here. Remember, we want a really weak acid to form. What's the weak acid I'm forming? It's ammonia. Okay, so we just talked about that. Ammonia is an ideal weak acid to form because its pKa is so high, it's much higher than the alkyne. Alright, so that means the reaction is going to be pushed two products because this alkynes are stronger acids than ammonia. Ammonia we don't even think of as an acid usually, right? We think of it as a base. So the reaction gets pushed to the right. That means amide is a very good base. It's going to be way more basic than the carbon with a lone pair to go backwards. Okay, this is the reaction that occurs to make alkynes. So I call it double elimination or double E2 because it happens twice. Now this is a constitutional isomer where instead of the 1,2 dibromide, I have a 1,1 dibromide, or whatever number it happens to be. Because these are generic R groups. I don't know how long the chain is, but anyway, they're on the same carbon. We call that geminal. So I don't know how many of you out there, what's your sign? I'm a Libra, but Gemini are twins, right? So Gemini, they're twin halogens, okay? Geminal dihalide. So you could actually do double elimination here as well because you have these two beta hydrogens. So go ahead and draw out the mechanism for this molecule forming this one. Similar to how we did up here. And don't forget, let's use sodium amide. Okay, if you want to just balance the equation, we got 2 bromides off using 2 sodium amides, and these became ammonia. Okay, and if you want to put NaBr instead of Na and Br separately, that's fine. So here's an explanation again of why sodium amide is used. So if this is a stronger base than this is, so it's going to go forward. How do I know that? Because the conjugate acids are the opposite. This is a stronger conjugate acid than ammonia is, so it's going to be pushed forward. So bottom line is you're going to basically see sodium amide much more than you're going to see sodium hydroxide in these reactions. Now you guys should be familiar with the concept of an excess of reactants. That means we have multiple equivalents, so it's not 1-to-1 necessarily, but I have multiple NaNH2s for every one of these. So mole ratios are going to be such that this is in excess. So if that's the case, let's find out how do we use 2 NaNH2s to get from here to here, and then if I had an excess of sodium amide, how do I get to here? Go ahead and practice that whole thing again. It's good to keep doing it, okay? And I prefer it if you guys just redrew this instead of just showing it here, but you know, that's just my preference, is just showing that separately. And a lot of students try to combine all this going on at the same time to go directly, but I'd rather you just do it in steps. 3 arrows is plenty for 1 step, okay? So don't try to do all of them at the same time. So the main point of what this is telling us is that if we use an excess of sodium amide, you're going to end up going all the way to the conjugate base, not stopping at the alkyne, but going another step because you have so much sodium amide. It's a very basic environment. In a basic environment, you have the basic form of all the molecules, right? So, well, you know, within reason, it depends on pKs and pKbs and things like that. But in general, we know that sodium amide is a stronger base than this is. So that means it's going to be able to pull that hydrogen off and go to this. So that means that if you wanted the alkyne, you wanted that H, then you're going to have to do a second workup step. And usually in the second workup step, you can use water. I mean, we don't want to use ammonia because it's already in ammonia, and remember, it's weaker than the alkynes. The alkyne's going to push forward. So what we need is something that's not as weak as ammonia. We need water. So this will grab the H from the water, and then we'll make this guy. And it'll still be basic because of hydroxide, but then we can neutralize that further. So what this means is sometimes you're going to see an additional water step just to show that this is going to be in its neutral form. And that's pretty much right here. I forgot I had it on here. Okay, so that's going to be like this. Okay, so now here's a critical thinking question. Look at what's going on in this following sequence. We have 2-pentyne, and it's isomerizing into a terminal alkyne. What? And then another equivalent, and we get the alkynide ion. So let's figure out what's going on here. Can you guys think of a mechanism, a way to push the electrons to get from here to here? And then I think you're pretty familiar with how we do that. We just did that. So go ahead and give that a try. See if you can do it without looking at the answer. Okay, so I expect some of you guys will be able to figure this out, and some of you guys just are not going to know what the heck is going on here, because I didn't show it to you yet, right? So how are you supposed to know? Well, in general, whenever I get stuck on the same kinds of things that you guys get stuck on, I always ask myself, what am I trying to do? Okay, so I'm trying to make a double bond, triple bond on the end. I want to make these carbons have pi bonds. So I need to start eliminating hydrogens to get these pi bonds forming here. So I want an E2 elimination there. So to do that, I know that I'm going to have to grab that. And so that's going to be one source of pi electrons, but what happens to this carbon? It can't have a double bond and a triple bond. So I'm just going to have to break that and put it on this carbon. So now try this, okay, as a hint, and then when you get that, see what else you can do from there. Okay, so pause it again and keep trying on your own. Okay guys, so here's my solution. Basically, I'm going to deprotonate here like I showed you. We're going to make this cumulene here, and then I'm going to protonate this. The only thing in solution right now I could protonate with is the ammonia that gets formed. So, or the solvent actually, ammonia. Now I just told you that this is not likely to grab a hydrogen off of here because the reactions actually favored the other way. Well, it's my only source of hydrogen, and this would rather get neutralized, if anything, so some small amount of the neutral product will form and then further react once it does, and then Le Chatelier will show that this will get pushed forward as we remove this from solution. As it continues to react, more of these will react until we eventually end up with this terminal alkyne. And then, of course, with excess sodium amide, we're going to end up with this ion. And then finally, what if instead of this stopping here, if I add a second water step, okay, then what I'm going to end up with is my alkyne.